So let's go to part 2, where I'm going to pretend to be Hennessy, which means I have to get taller and add gray hair. Right? So big changes. So the first part is kind of the challenges that we're facing. Big changes. The end of Dennard scaling. So Dennard scaling, as I'll show you, is you could add more. It was okay to add more transistors because they used less energy, and the power is constant. That's over. The ending of Moore's law. It's not like technology is not going to get any better, but it's slowing way down, not doubling at the rate that he talked about. Architecturally, we had some ideas of how to get more parallelism without the programmer knowing about it. That's run out of steam to be able to do that efficiency. And then how many cores can you really use? In Amdahl's law a long time ago, there's limited return on that. So if we look at process performance in the early CISC years, pre-RISC, it was doubling every 3.5 years. In the RISC era, it was doubling every 1.5 years. And those of us in the room remember when you would throw your perfectly working computer away because it was so slow relative to the ones you could get. That was the old days, as you will see. With the end of Dennard scaling, we had to go to multi-core, and it got doubling every 3.5 years. It slowed down, but not at the old rate. It still got better. Then Amdahl's law would kick in, and how much benefit you're going to get from multiple cores for most programs, not too much. And recently, the shocking thing, this is from the first figure in our textbook, is it's the end of the line. It's doubling every 20 years, 3% per year, shockingly fast. And so these days, you throw away your computer when it breaks, right? You don't say, look at your friend's computer and say, wow, I want to get one of those. It's a lot faster. It's not faster. It's the same speed. That's what's happened. So that's our first challenge, the end, a single program performance improvement. And this is just showing the ending of Moore's law with DRAMs. It used to be like clockwork, quadrupling every 3 years, and you can see it falling off there. Now, DRAM is special because it's based on capacitive filters, or trench capacitors, sorry. And so that's a special case. Here is Intel. If it had stayed with Moore's law, we'd have 10 times as many transistors today as we have on chips. So we're seeing the ending of that. So we're going to have to do something different. So that's the first challenge. And here's Dennard scaling, and you can see, like in 2008, where before it was pretty flat up to 2006, not the power per nanometer squared, and then it starts going up in 2008, going straight up, and now we're limited by power or by energy, which is what most architects think is the limit, not transistors. Okay, so that's the challenge. No more performance, ending of Moore's law, ending of Dennard scaling.